Now let's look at the last example problem in this topic. It's again a lead code problem. It's called data streams as disjoint intervals. So let's look at the problem from lead code. So given a data stream input of non-negative integers, so they come one by one, and the question asks us to summarize the numbers seen as using a list of disjoint intervals. So for example, if we are given this stream, so the first number is 1, so then that's a 1 interval 1, 1, 1. And the second is 3. So these, because they're not consecutive, so these are two separate intervals, 1, 1, 3, 3. And then we have 7, then 3 separate intervals. And then when we have 2, these two connect the first two intervals. So it becomes 1, 3, 7, 7. And then when we have 6, then that should be added to the interval 7, 7 and become 6, 7. So this is the problem. And this is identified as a hard problem. So in fact, I think this is actually relatively straightforward. It's definitely easier than the previous, the last example problem we look at. So first, let's think about how to do this in the straightforward fashion. And one straightforward fashion is we can make the adding the data efficient, and then returning the range query more expensive. So let me actually select a different language just to show the interface. So what we need to implement are basically two methods: add the number and then get intervals. So return the intervals. So we have two operations. We will get any number of them. So a trade-off is we can try to make one of them efficient, or try to make both of them to some degree efficient. So one approach is to make add number efficient. So we simply use an array, use a vector, and then each time we get a new number, we just add it to the end. And then when we are trying to get intervals, we first sort the number, and then we scan through the number, construct these intervals, and then return it. So this is one way to do it. It's very simple to do, so it's a very straightforward code. But this will not be efficient enough. So in fact, I submit this version, and then this times out, so which is to be expected. So then the second version is we maintain the intervals. And so each time when we add a number, we will update the intervals. And then because we are maintaining the intervals, this get interval method can be done fairly efficiently. So then the add number will be a little bit more expensive, but the get interval will be efficient. So I think the real solution should be using a efficient data structure for storing the intervals. But because the answer they asked us to return is an array or vectors, so then that means even if we maintain these ranges efficiently, when we return it, we still need to make a copy of it. So it still becomes inefficient. So we might as well just store these intervals using a vector. So then when we return it, we simply return the value we computed. But as we're going to see, this means that when we are updating the intervals, it will not be very efficient. But for this problem, the way it's set up, this seems to be the right solution. On the other hand, if the query we want is not to get the list of all intervals, instead of asking some intervals, then we shouldn't be using this data structure. So in fact, that's the last homework problem, is to change the query instead of getting all intervals, but getting the longest interval. So yeah, let's look at the solution for which version is this? No, yeah, this one. So this is a solution of maintaining a vector of intervals, and then each time when we get a number, we will update it. So and then when we ask to get interval, we simply return that. So when we are trying to add a number, we need to find out which interval could be affected. So in order to make that efficient, we sort the intervals in this vector. So this vector maintains a sorted set of intervals. Then when we add a number, we want to find out which intervals could be affected. So in here, I chose to search for the particular value. So if you ask me to add a number, then I'm going to find out which intervals will be affected by this number. So I use this lower bound call, and I pass in a comparator which will do the comparison for me. So this comparator will return true when the first one is considered to be less than the second. Because this lower bound function call is over a vector of int, and the query is the number we are flirting with a single number. So the first argument of this comparator function is the type in this vector. So it's vector of int, and the second one is the int value. And the comparison we check. I check the ending pointer. I check the ending point of an interval with this value. So once this lower bound returns, it returns the iterator, which will point to one of the intervals. And then there are four different possible cases for what I would do. So one of them is I will want to extend so actually let's put the case where they would happen. So the one case is so suppose we are doing add number, say 11. So then one case is these 11 will actually result in merging two intervals. So it'll be something to 10. We have something to 10, and then we have 12 to something. So this will result in merging. And another case will be we have no merging. We have the second one, but not the first one. So then this one will be less than 10. And then we have 12 here. So then this will be added to second interval. And another case is we will be added to first interval. So we have something 10, and then this other thing will be greater than 12. So this will be adding to first interval. And then there's I guess there should be probably 5 cases, but one case we don't need to do anything. So then there's a case where we don't have this, so we cannot add this to anything that's already in here. So then we need to insert a new interval 11, 11. So of course then there's another case which is this is already 11 is already included. So we have something that's start with a value that's less than or equal to interval to a value greater than interval. So then we do nothing. So these are the possible cases. So when we write these conditions to handle this logic, one way is to think about for each of the operation, what are the possible cases, and then we dig in and then do the cases. So that's how I wrote it the first time. But then I realized some of the subcases result in the same operation. So here, the code here is based on the eventual operation. So I first grouped the case 1 and 2 together. So because they both means the second interval, the interval that we find through this lower bound call will be this one. So that means it exists. So first this iterator must point to something, And second, it's start with the value value plus 1. So basically, we are checking this condition. So when this happens, then there are two cases. Then in either case, I can extend this first interval. So essentially, changing this to 11 in this particular case, and then I will check whether I need to merge. So if P has something before it, so if P is not the beginning iterator, then I can do subtract 1 on this iterator. And the second element of this interval, if it equals a value minus 1, so that's exactly this guy, then I'm going to delete P, and I'm just going to merge this into the previous one. So let's call this Y. So then what happens is I'm going to replace this as a Y, and then this will be deleted. So that's what this code is doing here. Yeah, so update this and then delete it. So that takes care of the first two cases. Now, if that's not the case, then we check the next two cases. So the previous one exists. If the previous one exists, and I guess really just this next case. So the previous one exists, and the previous one ends at 10. So that's this condition. So the previous one ends at 10. So then I just extend it to this. So I just change this 10 to 11. So that's here. Now I need to check this case. I need to insert. So insert this previous one actually doesn't have to exist. So, and also in fact the ones after it doesn't have to exist either. So if P does not, if this interval does not exist, that means we're at the end of this list, and we haven't found anything bigger. So that means we need to add this new interval at the end, so either P point to the end doesn't exist, or this interval start as a value that's greater than the current one. So in this case, then we just simply insert, because I know it can be extended to prevent. So this is because this is else from the previous condition. So this is take care of the case that we have to insert. So then else we don't need to do anything. So I don't have code for it. So that's take care of all the cases. So yeah, so the reason I said this is expensive is maybe you should think about which of these code could be, which part could be expensive. So the expensive part are this line and this line. So when we erase an element from the vector, if we need to move all the things before it ahead, so this could be a linear cost. And similarly, when we insert something, we need to push everything down. So this could be linear time. So whether this is expensive or not will depend on the data. So if the data result in many intervals, then this will be inefficient. On the other hand, if the number of intervals is relatively small, so that's what the follow-up question here. There are lots of merges and number of disjoint intervals small relative data stream size. So then this solution would be fine. But as I mentioned earlier, even if I try to make this insert and erase efficient, then what I need to do is to change this vector here into set. But if I change this vector into set, then anytime when I do get interval, I need to traverse the set to reconstruct this interval. So then that becomes expensive. So it doesn't seem to make sense. So again, the best solution actually depends on the kind of distribution we get. What are the data and how frequently are the queries? So this is what happens in real life development. So the best solution, it really depends a lot on the actual workload. So different design will have different trade-offs. So this question is a little bit similar to the homework question, but I think we can stop here.